Hello everyone and welcome to the next video of the states of matter. This will be the final video for the theoretical aspects. Okay, I hope you people are doing fine. You people are safe with your family. Do take care about yourself. Do take care about your mental peace, mental health and your physical health also. Okay, so let's start without ado. So for today we are going to look at various aspects such as what is vapor pressure, what it has a connection with the boiling point, what are the types of boiling point, further what is a viscosity and surface tension. Okay, so we'll start all this entire session with respect to the first point, and that is going to be let's start with the vapor pressure. Alright. Now, in order to understand as to what exactly is the vapor pressure, let's consider that we have a container. Okay, and let's say that this particular container is evacuated and it has been filled with a liquid. So let's say that this is the liquid that we have taken, and what we are going to do is we are going to seal this upper one. Okay, so when we observe this particular section, let's say this is a section of our observation. When we observe this, what we are going to have? We are going to see that there is a layer of liquid. Let's say this is the liquid layer. Okay. And on the top of this liquid layer, of course, what we have? We have air. Correct. Now, when we take a look at this particular scenario, the particular molecules which are at the surface over here, these molecules of the liquid which are at the surface, these molecules have sufficient amount of kinetic energy. They have sufficient amount of kinetic energy in order to overcome the internuclear forces, in order to overcome intermolecular forces. Okay, so therefore, intermolecular forces are nothing more than the forces which are acting between the molecules, right? So now, these have so much amount of kinetic energy that they are going to surpass, they are going to go beyond the magnitude of the intermolecular forces. Due to this particular point, what will happen is this molecule will not remain in the liquid state. Rather, because of the higher kinetic energy, they will slowly get into the gaseous states over here. Okay, now why this is happening? This is happening because our kinetic energy is far more than the intermolecular forces. Now, due to this particular condition, the molecules which are only at the surface. Okay, this is acting only at the surface molecules. So what is happening? The molecules which are at the surface, they have tremendous amount of kinetic energy, which is far more than the intermolecular forces. Due to which these particular molecules at the surface, they get into the vapor state. Okay, so all these particular molecules over here are in the vapor state. Now, how many number of molecules, that is the number of molecules per unit volume, per unit time, which are getting converted from the liquid into the vapor state, this is called as the rate of vaporization. Okay, so here what is happening? These particular molecules, how many number of molecules per unit time, per unit volume, they are getting converted from the liquid to the vapors. We call them as the rate of vaporization. At the same time, what is going to happen is these molecules have sufficient amount of tendency. They have sufficient amount of tendency in order to associate back into the liquid state. Some amount of the particular molecules are going from the liquid state to the vapor state. At the same time, some amount of these particular molecules have the tendency to get associated back into the liquids. Now, this particular process, we call it as a process of condensation. So here what is happening? It is a condensing. Okay. So therefore, there will be a time where the rate of vaporization and the rate of condensation will be same. Okay. So that means when we have a particular liquid over here, the amount of molecules which are getting associated that is nothing more than the condensation. Right, they are getting condensed back. So, how many number of molecules per unit time, per unit volume, that is getting condensed. We call it as the rate of condensation. Okay, at the same time, how many number of molecules from the liquid are getting converted into its vapors? This particular process we call it as vaporization, right? And how many number of molecules are they getting vaporized per unit volume? Those we call it as nothing more than rate of vaporization. Okay, now let's try to understand. There will be a point in all the type of liquid systems where these particular, that is the rate of condensation, will be equal to the rate of vaporization. Okay, now at that particular condition, what is the pressure? What is the pressure generated by these vapors on the liquid, on its own liquid at the constant temperature? That particular pressure, we consider it as a vapor pressure. So, a vapor pressure is nothing more than the pressure exerted by the vapors of on its own liquid at the equilibrium, at constant temperature. Okay, at the constant temperature is called as the vapor pressure, or we can also call it as a saturated vapor pressure, or we can also call it as equilibrium vapor pressure. Okay, so what we have here, at the equilibrium, at a constant temperature, the pressure that is being generated by the vapors on its own liquid, that is called as a vapor pressure. Okay, now let's understand as what it has a relation with the boiling point. Now, let us say that we have a particular container, and in this particular container, what we have is a liquid. The liquid has its vapors. Let's say these dots will represent to us all the vapors over here. Correct. Now, as we take this particular thing, we know that this is a surrounded. Okay, let's say that this entire thing over here is surrounded. Now, in the surrounding also, what we have pressure that is being generated. Correct. Now, this pressure which is being generated in the atmosphere, we will call it as nothing more than the atmospheric pressure. Now, you need to understand that the atmospheric pressure is far more than the vapor pressure at these normal conditions. Okay. Now, as we start to heat this particular container, what is going to happen is more amount of these particular molecules from the liquid will start to get converted into the vapor states. or simply they will move from the liquid states into the vapor states. Correct. Now, due to which the amount of the vapors collected over here increases. Naturally, as the vapor collection increases, the pressure on this particular liquid also increases. Now, at that particular temperature, wherein the vapor pressure becomes equal to the atmospheric pressure, and that particular temperature, we call it as the temperature where this particular liquid starts to boil. Okay, so basically, the temperature where the vapor pressure of the liquid becomes equal to that of atmospheric pressure. Okay, now when it becomes equal to that of the atmospheric pressure, this is a condition where our liquid will start to boil. Okay, so therefore this is called as the boiling point. Right? Now, there are two types of boiling point if we have to understand this very well. It all depends upon what is the pressure or how is this particular pressure measured. Okay, so we have the first one, what we call it as the normal boiling point. So at the normal boiling point, what happens is that here the pressure that we are measuring, this particular pressure is taken in the form of atmospheric pressures. Okay, so whenever we measure in form of the atmospheric pressure, we consider it as a normal boiling point of a liquid. Okay, so for example, normal boiling point of water, if you do consider, it is 100 degrees Celsius. Okay, now I said that how do we measure this particular pressure? Whether we are measuring it in form of atmospheric pressures or whether we are measuring it in form of the bars. Okay, pressure can be measured in two ways. In this particular scenario, we are going to take with respect to atmospheric pressure or we are going to take it with respect to the bars. So, the second point what we have is the standard boiling point. So when we consider the standard boiling point, what happens here is the pressure that we have of the surrounding, that particular pressure we are going to measure in terms of bars. Okay, so at that particular point, whatever the boiling point becomes, it is called as the standard boiling point. So therefore, standard boiling point the standard boiling point of water. Now this one is 99.6 degrees Celsius. So this is how it slightly varies. So in examination if they ask what is the standard boiling point of water, it is going to be 99.6 degrees Celsius. While the normal boiling point of the water is going to be considered to be as 100 degrees Celsius, and that is what the main difference is. Okay, so it all depends upon the surrounding pressure. How do we calculate it? Whether we calculate it in form of atmospheric pressures or whether we calculate it in the form of the bars. Okay, that's how it is going to vary now. Done. So let's go with the next one. And the next thing that we need to study is called as the surface tension. Okay. Now, in order to understand this particular surface tension, let us say that we have a slide here. Okay, a glass slide. And on the top of this particular glass slide, let us say that we are going to drop a particular drop of water. Okay, so we have a drop of water here. Now let's understand why this particular thing has a spherical surface. Now, let's consider in this particular drop two conditions. When we magnify this particular thing, what we have? We have this is a surface, correct? Now, let's consider two conditions. Let's consider a molecule inside the water and let's consider a molecule on the or near the surface of this particular water. These are the two conditions, right? Now, whenever there is a molecule inside the bulk in a sense, inside this particular water sphere. So, what will happen? It is going to be surrounded by certain number of water molecules or the liquid molecules. Is it right? Now, these liquid molecules as what we have, these liquid molecules over here will attract these molecules from all these sides. Okay, due to which the force of attraction which is being felt by this particular molecule. Okay, so the net force over here is going to be zero as what is being felt by this particular molecule. Same exists in all these particular conditions inside the bulk. This is happening in the bulk. Bulk in a sense inside the water system. But that is not the case when we see the molecules on the surface, near the surface. Okay, so near the surface, what will happen is these molecules will surround it over here like this. But there are no molecules to surround on the surface. Due to which these molecules on the surface will experience an inward pull. So these are the molecules which are experiencing an inward pull. Okay, as it experiences an inward pull, what will happen? These molecules will start to go inside. Correct. So as a reason of which, any particular liquid that you drop, it is going to have a certain type of a spherical surface. Okay, and that spherical surface or the spherical nature is because of the inward pull that has been experienced by the molecules at the surface. Okay, because of the unbalanced forces that has been created at the surface. So here, all these over here at the surface are unbalanced forces that are been occurring here. Alright, so this is a condition as what a particular molecule at the surface feels. So this particular phenomena is called as the surface tension. Okay, and this is responsible. This thing is responsible for the spherical appearances of liquid. Okay, so this is one of the points. Now, surface tension is usually denoted. It is denoted by gamma. Okay. It is expressed in a form of Newton per meter. So you have to remember this. Alright. So now let's say that we have two types of liquid. Let's say this is one particular liquid which has been taken over here in this particular container. And let's say that there is another liquid which is over here. Something like this. Okay. Now, at this particular liquid surface, if we draw a line, let's say this is a line that we have drawn, correct, to the surface of a liquid, and now this is a perpendicular perpendicular which has been drawn to that particular to that particular straight line. Correct. Now, let's say this represents to me 1 unit. This is 1 unit length. Okay, from here to here. So the force which is acting perpendicular, to the line drawn to the surface of that particular liquid is called as surface tension. Okay. Now, if we do consider the same statement here, let me say that if I am going to take this area, now this is a straight line what I have drawn, correct? So, let's say this is a straight line what we have drawn and this is 1 unit length. Now, if I am going to draw a perpendicular is going to be something like this, correct? Now, at this particular perpendicular, the force which has been exerted, the force per unit length, perpendicular to the line drawn to the surface, okay, to the surface of the liquid, that particular force we call it as the surface tension. So if we put forward this into entire statements, it is going to be as the force per unit length perpendicular to the line drawn on the surface of the liquid. This particular force that has been exerted, it is called as the surface tension. And surface tension is given in the form of gamma and it is expressed in the form of Newton per meters. Okay, so this is all about the surface tension. So let's start with the last point for today, and that is going to be the viscosity. Now, in order to understand the viscosity, let's say that we have the slides which have been placed something like this. Let's say these are the glass slides. Okay, so let's say all these particular glass slides are inclined at a particular position, right? Now, if I put a drop of water over here, okay, and if I put a drop of oil over here, and if I put a drop of honey over here, now it is quite understandable that the water is going to flow. The water flows through this glass slide very fast. Comparatively, this particular oil is going to flow, but of course the oil is going to flow a little bit, you can say, as with a lesser velocity. Okay, so this particular oil flows, but the flow is with a smaller or less velocity, while honey flows the slowest. Correct. Now, this particular phenomena, that is the internal resistance of the liquid to the flow of it, is called as the velocity. So, if we want to define a velocity, the internal resistance to the flow by the liquid. This internal resistance to the flow by the liquid itself is nothing more than the viscosity. So quite naturally, higher the viscosity, slower is the flow of that particular liquid. Quite simple as that. Okay, now in order to understand this particular term viscosity in much better manner, okay, what shall we do is, we will try to take a particular glass tube. Let us say that this represents to us a glass tube. Now let's say this is a glass tube. Now over here, let us say that we are going to inject a particular type of liquid. Let us say that we are going to take over here honey. So when we take honey and when we push it inside, what is going to happen is that this honey, as it starts moving, what will happen is there are going to be several layers which are going to be generated while it is flowing. Try to understand. Let's say this is our first layer. Okay. Let us say this is the first layer. And usually when a liquid is starting to flow, the first layer which is in a contact with this wall, this first layer usually stationary. That means it is not going to flow. Okay, it remains stationary there. But as we go on the top, let's consider this as the second layer of the same liquid. Okay, when it's flowing, it's generating several layers. So when the second layer comes over here, this layer flows. It flows with certain amount of velocity. Okay. Now, this one, let's consider this is as a second layer. Of course, this layer flows with certain amount of velocity. Now, as we go to the topper layers, as we go to the adjacent layers, what happens there is the velocity goes on increasing. Okay, there is a regular increase in the velocity. Let's say this is the third layer of the same liquid. Okay, now this particular liquid flows at much more greater speed. Okay, so in order to understand this in a mathematical way, let us say that this is the third layer. This is the second layer of the liquid which is flowing. And let's say that this is the third layer which is actually stationary. Okay, now when we consider a viscosity, now let's say that if this is a black color layer, that is the second layer, is moving with a velocity as u. Okay, now this one has the velocity less with certain amount. We will represent that certain amount as u minus du. Du represents a particular velocity which is quite less. Okay, let's say that this is a layer that is having a small amount of higher energy, okay, than the middle one. So plus du. So this graduation, a gradual decrease or the gradual increase in the velocity, we call it as the laminar flow. So laminar flow is nothing more than the gradual increase in the velocity between the two layers separated by certain distance. And let's say that certain distance which has been, these layers are separated, let's say that it is as du. So du will represent amount of separation between the layers. So dz will represent amount of separation, the distance of separation between the two layers, and du will represent the velocity differences between the two layers. Okay, so that particular thing we call it as the laminar flow. Okay, now the force which is required, in order to maintain the flow of this layer. Okay, so the force which is required to maintain the flow of layers, okay, which is required in order to maintain this flow of layers, is directly proportional. It is directly proportional to First thing, it is directly proportional to the area which is in contact. Okay, it is directly proportional to the area in contact and the velocity gradient. Therefore, the force is directly proportional to the area into the velocity gradient. So therefore, we can write it down as the force is directly proportional to the area into du by dz. So du by dz is nothing more than the velocity gradient. A, of course, is the area. Now, if we remove this proportionality, we are going to have force is equal to eta into A into du by dz. So this N over here is the velocity coefficient. Okay, so this was all about the viscosity. Okay, so I hope you have understood about the viscosity. If there is any problem, you can message us. Do take care, stay home, stay safe.